Good morning, good afternoon, good evening, depending on where you are. Today, we're gonna go through a project to build a machine learning model to predict loan approval based on characteristics of loan entries. So, what's our game plan for today? So, first off, we're gonna introduce the scenario and then we will do the initial data examination, data cleaning, a developed model, and our preferred tool for today is going to be Python. So, what's our scenario today? Well, imagine you're working at a certain bank or a financial system consultancy firm, and then the head of research or the head of the retail credit department he comes or she comes to you and asks for your support as a data analyst to help them understand the dynamics of loan approval and what determines loan approval or the highest impact or the most impactful characteristics, let's say. And they have a database for you consisting of 32.5 thousand applications. Some of them were approved, some of them were not. So we are going to go through 12 features in the data, basically 12 fields, 12 columns, to see what factors have contributed to loan approval. Of course, initially we have to import the database. We will also explore statistically, rather an overview of properties and credit history, the client demographics, the distribution of the data itself, and the description. And then we will clean the data. We will see if there are any missing values, the correlations as well. It's most appropriate to use correlation to handle missing values at certain points. So we'll go through that as well. And then finally, we will create the model that can predict loan approvals on the basis of a fitted model that we will fit together. Of course, the model will have multiple applicability in risk assessments and financial forecasting and credit scoring. So we will create the model, we will compare the different fits, and then we will use it to predict values and also to monitor the features and their importance in approving loans. So with that, let's move on to Python and see how we go through this process. So here we have the Python code for the project. What I like to do generally is to chop up the objective into certain deliverables so they are easier to deal with. So basically I set out three deliverables. Two of them is basically for myself, and the third is the deliverable that we will actually deliver to the stakeholders. The first is the exploratory data analysis, where we kind of want to see the insights and visual representations of the data. And then the clean data, which addresses any issues that we have with data. And then finally, the machine learning model itself. Of course, as always, you'll find this code on my portfolio. Possibly, I always link the portfolio. I always link the YouTube channel and different things down below. So you will find this as is. You can copy and edit it as you wish. Okay, so we'll start by importing libraries. Well, first off, the one that needs highlighting is PyCaret. We will need to install that. So use exclamation point or mark pip install PyCaret. The rest are rather standard. The pandas is what allows us to deal with data frames within a Python environment, and the Seaborn is matplotlib as well, are both like for the visual representations. Maths for doing calculations, and missing no is the one we will use to deal with data. NumPy is also for statistics and calculations. And warnings, of course, is just because like certain warnings pop up that are irrelevant for us. And this is just the installation of PyCaret. It will run through the same project, the process for you. If it gives you these red things, it's okay. It's fine. We will deal with them as we go. So the first thing is, excuse me. The first thing is we import the database into the data frame. Since I'm using Kaggle here, I inputted the file as an input for the notebook itself, and then used it and used panda.read underscore CSV in order to read the file into a database. So let me move on to the Excel sheet first to see what we're dealing with, and then we can come back and do the exploratory data analysis. All right, so this is the database that we will be using, the 32.5 thousand entries. We won't go through all of them, of course, but it's nice to just see the columns as is and try to interpret and explain what each one means. So the person age is self-explanatory. Person income is also okay. So the person home ownership seems to be a categorical column where we see whether the person is renting, owning, or has a mortgage on their house. The person employment length is the length of which the person has been employed. Of course, I note here that this person has been employed for 123 years, which is, that guy must be, and he's 22 years of age. But that the funny thing is that fits today's market requirements to be hired. You have to have 123 years of experience while you're 22 years old. And then we have the loan intent, which is what intent basically the person is borrowing for. Also seems to be a categorical column. The loan grade, the loan amount, the loan interest rate, which I'm assuming that it relates to the loan grade, but we will see how much they correlate in our examination. And then we have the loan status. This is just a Boolean column, whether or not it has been approved, so 1 or 0. The loan percent income, so I'm assuming this is the amount of the loan as a percentage of the income. And the CP person default on file means whether this person has historically defaulted or not on loan. And then the credit history length is how long he has had the credit history. So now we have a better understanding of the columns that constitute our database. We can return to the Python code and see how we go from there. Okay, so coming back to the Python code, we have first we're going to perform the exploratory data analysis. The first thing I like to do usually is to check into the data type consistency to see if the columns are actually consistent with the data type that they present. So basically, the biggest issue we are facing on the data front is we have some columns that we would need to treat them as categories and others that we need to treat as Booleans, but they are not in fact being done so. So this is, for instance, is being an object, the one we saw yes and no before, and loan status is an integer. It's a Boolean value, as we have seen in Excel. So basically, let's take the person home ownership, which is an object. It's not a category here, so we need to deal with that. Loan intent, which also seems to be categorical, is classified as an object without any additional clarification of the data type. Same with loan grade and the person on default and the loan status. So what we are gonna do is basically ask it to register this or define these columns to check. And then we will use a for loop to check the columns in this number of columns. And we will ask it to print the distinct value in each one of these columns and print the unique values that come out through, so we can see actually whether they are categorical, whether they are, which we already know, of course, seeing as how we have seen the Excel, but we also want to have clarity whether there is any unexpected values. So identifying the unique values is very useful for that. So the next step is to fix the data types. So we're using this code to transfer person, home ownership, loan intent, and loan grade into category type data, and the person default on file and loan status as a Boolean value. And then afterwards, we just check if the changes have actually taken. And we do see that now we have 3 columns which are categorical and 2 which are Boolean. So with that, now we can kind of know that we have the needed entries in the right data type. And moving on, then we can start to sort of take a look at the data for the numerical fields particularly, see how they are distributed. We can use the f.describe just to see the central tendency measures and the IQRs. But of course, it's much more helpful to get a visual distribution or a visual representation of it using this code. So basically what we do, we identify this call, which is like basically the numerical columns that we have here. And we start working on the shapes basically. So set up the visual columns per row. I want to have 3 figures per each row. And the number of columns themselves is the length of this call. So whatever number of these 1, 2, 3, 4, 5, 6, and 7 of them. And the rows, this is where we use the math. It's just calculating the ceiling. Basically, the number of rows that we are going to need, which is the number of columns divided by the column per row. But then they round it up, basically. The ceiling function rounds it up. Then set up the figure axis, basically using Plotly. And then we make a for loop for each variable, and we enumerate it using I. And then we can kind of just use the SNS to make histoplots of each column. We would like them to give us also the density distribution, which is the line that you will see there. And this for loop is just to deny the existence of any other like columns, so you don't get these like x and y axis, even though they're empty. So this kind of takes care of that, the dlax function. Okay, so then let's take a look at the distribution that we have. We don't even see anyone that is nearly normally distributed. The loan percent, an argument could be made for loan percent income being sort of normally distributed, even though it's skewed to the left quite a bit. Everything is specifically in the person age, the person income, and the person employment length. All of these are rather, distributed to the left, and then that implies that we have outliers, really significant outliers. So we can take that forward and just take a look at it. Okay, so basically we're going to use a box plot. We will follow some similar code to the one before. We're only going to focus on the 3 that we have mentioned that really look like they have outliers: person age, person income, and employment length. And then we will set the excuse me, and then we will set the box plots, the subplots for it. using again a for loop and another for loop to take care of anything else that if we might have had like other visuals, then we have kind of takes care of that. And we do detect the person age, just as a it's implausible to have someone who's 120 something and 140 something, and then the person income here is also quite a bit outliers. So you can here suspect like this is how many times of the maximum. This is like two times maybe of the maximum, to 2.5 times or something. So uh, must be an outlier. And the person employment length says someone has been employed 123. We already saw that in the Excel sheet, so we are going to need to deal with these things. So we will deal with the implausible values in the numerical fields. So we will first outline the implausible entries. We will set our maximum for a person's age at 100, the person income at, what do we want to say here? Was that like 3 million? And the person employment length is set to 100. Yeah, and then we will anything more than that, or this sign signifies or when we are using a data frame, or basically addressing a data frame in pandas. So this sign signifies an or. Likewise, this. So these extreme values, you can of course deal with it in a number of different ways. You could impute the values based on mean, but for me, in my opinion, I thought we have 32.5 thousand, dealing with how many, 1, 2, 3, 4, 5, 6, 7 of them, and that are like kind of just not fitting with the data, is we can just easily toss them. Person's age 144, 444, 123, 144. No. This is too much. And person employment length also. So we cannot really kind of venture a guess. I do not think that's the best way. Of course, you can, as I said, replace them with the mean. Replacing them with the median is better in this particular case, since the data is quite skewed, not really normally distributed. But anyway, I chose to drop them. So I was dropping the implausible entries that we had, and then resetting the index, because if you don't reset the index, then you have a bit of a weird range index here. It just messes with your data a little bit. So starting from now, basically we have df2, and now df2 is an entirely a new and better data set. And of course now we note some things, of course, like we have missing data, which we will get to, obviously. But first, we can take a look at the category and the Boolean data first. And using the df2 that we have created after dealing with the implausible values, we would like to describe the category and Boolean values, just so we see, of course, there's a difference between using the describe function on American categories, on numerical columns or categories or whatever, and there's a difference between using it on the category and Boolean. So here it gives us the count, the unique number of entries, the top entry, and the frequency of each. So I like to again see things visually. It's good practice and it gives us insights. So basically, this looks a bit complex, but it's just like generally we take the categorical columns, we set the plot up similar to as what we had, and then the tricky part, it just gets a little bit tricky, because I would have liked to create a stacked bar plot. This is why, you got the unstack, fill value equals 0. And then when you plot a stacked bar, you say, well, stacked equal true. And the color, of course, choosing the colors to be representatives. And all these is just formatting for the charts. So basically, what I want to elaborate on this particular form of visual representation, you kind of get a feel for it once you've made once, twice, and three times. You kind of already know what to do, and based on that, you just go to your repertoire that you have had already done certain visuals, and you just copy and paste the code and then fix it to fit the data frame that you have right now. So I'm not going to go through each and every level of this, but I will say that it is a lot easier than it seems once you've done it once. Feel free to just go to my code, steal it. I'd be happy if it is beneficial. And then we have here the distribution of the categorical and the distribution of the Boolean data. And what we can see is basically what we can conclude is the approval rate for rent is higher than for other ownership options. We can see that reflected here. The true values is, a large majority, the highest percentage out of all the columns. That consolidation is more likely to be approved than other landing. This is fine. We can see that here that consolidation tends to be agreed upon. We can also say the medical, by the way, is an option that tends to be agreed upon. And the loan grade D here is usually more approved. And if the person defaults, then for the most part they will not have the loan approved, but a certain percentage will have their loan approved. So then moving on, the first step, I think, standalone understanding correlation is very important. On a second front, though, on an additional benefit, on a meta level, we can also use it to address missing values. So what I did here is I want to have the data frame with dummies. Why is that? Why is that? Because correlation functions do not really handle categorical data very neatly, very nicely. So I need to get the dummies where the values are 0, 1 for each entry so that I can actually understand the correlations and be able to address the data on that basis. So for the person home ownership and the loan intent variables, we can do the pd.getDummies. And then we drop the first entry so that we don't have like a one-to-one correlation or something that messes with our data. We just drop the first entry of it. And then the one hot encoding, basically it is same for long grade, but the only difference is why we did this A7, B6, C5, and so forth, is because there is a meaning to the arrangement of the data. It's an ordinal variable. It's categorical, but it's ordinal, it's not nominal, meaning that there is a certain order implied. A is higher than B, B is higher than C, and so on and so forth. So basically, we take afterwards the data frame with the dummies, and we take a look at it just to see the info. And then we ask it to, here we can see the dummies we have, and everything that we have just done. And we tell it to please plot the figure sns.heatmap. We'll use sns to see like kind of a heat map. We can do the correlation like matrix as in a table, but we won't really be very happy with just numbers. So we'd rather they kind of paint them for us and visualize it in a better way. And again, this you will use multiple times. So no problem on that front. And then we have the correlation heat map here, starting from like -1 to 1. And what we want to see is the absolute values, not necessarily the directions right now, but just the absolute values, how they affect one another. So the two, okay, so we have here first, if we go like that, well, person age relates to the person's credit history length at 0.88, strong relationship. We have the loan grade relating to the loan interest rate at negative 0.93, which is very important. And as we highlighted, we see that loan grade is very highly related to correlated to loan interest rate. So we'll have to address that if we are going to perform any statistical work, which we will see how we can do that. And then we have negative 0.85% home ownership mortgage and rent. This is just because we'll ignore this relationship because it's two like dummy variables that we extracted from the same like comprehensive variable. So what we can say is that we note a high correlation between the loan grade and loan interest rate, followed by credit history length and age of borrower. There are other relationships we can disregard. They're not as high or not as informative as having an absolute value of bigger than 0.3 or greater than 0.3. So on that basis of the correlation, we can start to handle the missing data. I love this. The missing no package is very useful and helpful. So we use msno.matrix. We give it the entry. Enters the data is df2. Fixed size is just, if you don't do the fixed size, it's just too big and it kind of messes with the way you see things. So I like to have all the information in front of me. So we see here, okay, so person employment length, it has some issues. We have loan interest rate, which has some issues as well. So the neat thing is we can fill in the missing values using fill NA. Okay, so we just tell it, have this database, we have this column. I'd like to fill the non-available values with, here, basically, we are telling it to group by the loan grade. So all the loan approaches that has a loan grade of A, put them together. All the ones that have a loan grade of B, put them together, so on and so forth. And then for the loan interest rate, transform the non-available values into the median of these groups, and do that in place. You do not have to kind of create another column or anything. Just do that in place. So we use the loan grade based on the high relationship 0.93 absolute correlation with the loan grade. So loan grade is related to loan interest rate, and now we utilize that relationship to impute the values. On the second front, we need to impute values for person employment length, but we choose to do that based on its own median, person employment length. Yeah, so let's take a look here, person employment length. Yeah, there is no particular high correlation except for with itself, of course, which is we ignore. So on that basis, we don't really have any correlation that can kind of inform the imputation for person employment length. So we choose to fill in the non-available values with the median in place. And now we have our clean data set, basically. We've addressed the implausible values. We've conserved, the outliers within logical means. We've addressed correlation, imputed the missing values. We have a good data set now. So we can we can use this command of pair plot based on loan status and show the distribution. But the idea is it takes a long time and a lot of resources. So I kind of hash it out once we are doing something else. But it could be useful if you are trying to explore the data further after you have cleaned it to use this function. And then we have our machine learning model that we can utilize based on the entries that we have from our clean data set. So for our machine learning model, basically we'll be using PyCaret. PyCaret is basically a library or package where you can use not that much code, but still get the machine learning results that you would need. And it has a very robust setup design where you can actually identify a lot of the parameters that you would like to utilize in the machine learning model. On that basis, we import the PyCaret classification and we go ahead with the setup. As you remember, we have dealt with the kind of improbable or implausible values, but we have not addressed particularly outliers. In certain situations, you would need to address outliers and focus on them, getting your data kind of normalized. But when it comes to financial data, things are a bit more complex. So we do not want to sort of take away from the variation of the data set. It's a bit of a compromise. You always have a trade off. So basically, what we are going to do instead of taking care of outliers ourselves, we're going to use a normalization method that is more robust, which suits better data with outliers. So basically, we're going to set up our model. We are going to tell it, use the data from the DF2, which is the clean data set that we have. The target that we would like you to aim for is the loan status. So I want you to predict the loan status. And I want you to normalize the data set using a robust method which takes care of outliers, or at least addresses outliers. Nothing can take care of outliers. We also have seen instances of multicollinearity. So in that case, we set it to remove multicollinearity, deal with it somehow, and your threshold is 0.85. We have seen that we have 0.88, we have seen that we have 0.93, and so on and so forth. So we're going to tell it your threshold is 0.85, which is fair. And then you set the session ID, which is important for kind of replicability, and it is, I believe, is necessary to run the setup. And once we run that, we have our setup of the model. So it tells us this is a session ID, you're targeting the loan status. The target type is binary, is 0 or 1. The original data shape is you have 32 inputs and 12 columns. We transformed it into having 25 columns since there are some that have, categories. We have numerical features of 7. We have categorical features of 3. All sounds good. We pre-process the data. We're imputing data simply. Of course, they don't need to do imputation because they supposedly have all. Numeric imputation is mean. Categorical imputation is mode. They don't need to do that because there is no missing values. We've addressed that. And remove multicollinearity, yes. Threshold is 0.85. Normalize, yes. Normalization method robust. Um, and the fold number for us is a stratified k-fold is a generator, and we have 10 folds, and so on and so forth. And then, so it tells us, we've already did that. In order to train our model, we took 22,801 entries, and in order to test the set, we have tested it on 9,773 entries. So the next thing is, we want to see like which model that it used in order to generate the machine learning outcome, and also the comparison of the different indicators of its accuracy, the area under curve, recall, precision, F1, kappa, and MCC, and the time taken as well. So it seems like it is, for us, it is recommending we use the compare models function. It just reads immediately the model that you have created, and it gives you the different models and gives you the different results. So we have here high accuracy. The area under curve is the extreme gradient boosting. So you basically have to set some criteria for yourself. Usually we take accuracy, we focus in an area under curve, we focus on the F1, which is basically the mean of precision and recall. And the time taken, of course, if you're dealing with a huge data set. So basically, for now, we can count on the accuracy and precision. If someone else would like to solely focus on the AUC, we take the extreme gradient boosting. Although the difference is not so much, it's like 0.0002. So, we can still go with the light gradient. And the precision is highest here. Again, the difference is not so huge between CAD boost and light and the F1. Kappa, same, MCC. We win with the light gradient boosting machine. So we're going to use that model in order to sort of create our predictions. So we'll name an LGBM underscore model and create the model based on light GBM. Here, we just, use this acronym. And this will be our model. This is how the machine learning process would attempt to address any data set that is introduced to it. Once we run it, we can see the mean. We have a high means. Lovely. We have low standard deviations, which is also awesome. That's what we are looking for. And then we try to predict the model. The full DF2 is basically we predict the model based on fitting this model that we have created here with the data from the DF2. And the model, it will tell us, well, the model is light gradient boosting machine, and we have our full DF2 with 32,574 entries. But here, what we can see they added is the prediction label and the prediction score. So let's look at the head. The prediction label is basically whether or not the loan status is predicted to be false or true. And the prediction score is how highly are the chances, or how high the chances of the prediction label actually being correct. So we can see here that the loan status is false, for instance, for this entry. The prediction label is 0, so good, so far so good, and the prediction score is high, is 0.97. So we're doing very well, and the same for the next entries as well. And we can save that as CSV. This will be our final predictions. Of course, this is just the head, so it gives you like 5, I think, rows, 5 entries. But we have, as we said, more than 32,000. So we should take a look at the CSV. We will ignore the index. We don't want it to re-index the entries. Just, do not use an index. Just leave it as is. And finally, to plot the model of the features, we just want to see it visually. How important is each column in determining the loan approval per the machine learning model? It says to us, oh, personal income is the highest and most important. The loan interest rate, so the pricing basically, is very important for approval as well. And the loan percent as part of your income is the third most important. The loan amount is also important. The employment length, credit history length, ownership being rent, ownership being own, loan intent being medical, or loan intent being that consolidation, which reinforces the results that we had come up with from our exploratory data analysis. So this is very good results, very important results. These are things that we can share with the stakeholders to kind of, enable them to have the knowledge on, okay, so when to expect a certain loan will be approved or not. Of course, it needs a big data set to come up with such predictions, but other things being constant, we have these features that you can look at and kind of estimate whether or not a certain loan would be approved or not. That has been basically an exploration of the code, how you would address something like this, where someone in the banking industry is coming to you to understand or find out the different determinants of loan approval, and how you address that based on data with the data-based approach, how to create a machine learning model, and how to expect to use that model to predict whether or not loans would be approved. Well, I hope this has been useful, and thank you for following through with me to the end. And please, if you have any comments, any additions or edits that you would like to share or propose, please feel free to comment. Link down below, you'll find my portfolio, some other work, some presentations that might grab your interest. Thank you for watching, and happy analyzing, and see you in our next video.